Today's talk is going to be about error handling patterns in Apache Pulsar. So my name is David Kjerrumgaard. I'm a developer advocate at StreamNative. I'm also a committer on the Apache Pulsar project and author of Pulsar in Action by Manning Press. I previously also contributed to the book Practical Hive and have extensive experience in software development, big data, and streaming. So today I want to cover three things at high level. First, we'll cover stream processing semantics, get into some definitions and talk about what they mean. Then I want to introduce a Pulsar error handling demonstration framework that I developed to better illustrate some of these concepts in real life, to get an understanding of how messages flow through the system and how they get processed during these error conditions under various configurations. And then after I've introduced that framework and I run it through examples, I will discuss the results and introduce some of the error handling patterns and discuss some of their pros and cons. So let's begin with stream processing semantics. In an ideal world, stream processing looks something like this. Data is continuously coming into your application. It's being processed in the order that it was received. No processing errors occurs, and life is good. Everything's processed exactly once. No errors happen, and life is good. But in reality, things happen. Unexpected errors happen. Systems go down. Connections go down. Data in the topic is bad. So how do we handle some of these situations, right? When there's an error, how do we handle these things? That's really what the focus of today's talk is about. So what are some of the things that could go wrong? Well, all of these things here. You can have everything from an external system outage to data corruption within the messages themselves, application bugs. You make a fix, deploy your application out there. There's a bug in it, networking issues, hardware failures, messages get lost, latency spikes, any and everything can happen. So there's lots of things that could happen. But to think about them in more concrete terms, or sort of put them into classifications or buckets, we usually consider these errors across three different key aspects here. First being the breadth of the impact. What percentage of messages does this error impact? So going back to the previous slide, example like bad messages, that scope or breadth of impact is just one single message. If you have corrupt data, it's just going to impact that message, and other systems, the next messages will be able to be processed, and there's not going to be sort of issues. Next is the duration of impact. How long will the processing be impacted by this error, and how long until it's resolved? So this comes into play for things like networking issues or hardware failures, things like that. How long is it going to take? How long am I offline? How do we start buffering messages in this scenario? How are we going to recover those sorts of things? And then last but not least is the resolution method. Or does resolving the error, can it be done manually, or will it resolve itself over time? These are some of the key things to consider when you're thinking about errors and the types of errors and how to process them. And so based on those aspects, again, this is a very loose approximation, but you can basically classify errors into the category of transient or non-transient. Right? Transient errors are those that that resolve themselves very quickly, don't require manual intervention, and the mean time to resolution of these types of errors is generally very low. Whereas non-transient errors, again, either require manual intervention to be fixed, or take a significant amount of time to be resolved. Right? So if you go back again to our word cloud, transient examples are something like, intermittent network issues. Those will go away. Don't really require you as an application developer to get involved and fix these sorts of things. Whereas a non-transient error would be something like a bad message or corrupt message. That's something you can never correct, really. You can have a system send another copy of the data, but for as far as that message is concerned, it's unfixable. You can't resolve it. Again, it has limited breadth, but it is a non-transient error. There's nothing you can really do about it. You just have to figure out how to deal with each of these in your error processing systems. Right, so breaking it down across these different sort of characteristics that they have. Again, examples of transient errors are networking issues, an external system outage. Let's say you're processing the data off a topic, persisting the data to a database, maybe publishing into another system for order handling, things like that. If that system goes down for a while, your application can't interact with it. That becomes a transient error. Expired credentials is something that can be fixed. Missing data in an external system, you're trying to do a lookup into an inventory system on that data and it's not there. If you wait a little bit of time, will it resolve itself, right? Maybe if you try again in 30 seconds, the data will be there, life is good. Non-transient errors are, again, things like malformed messages. You have an encrypted message and you've lost a decryption key. You're not going to be able to recover that. An application bug is something that's going to require manual intervention. You release some bad code, it can't process the messages. And obviously hardware failures. If something goes down, you can't easily recover from that without manual intervention in some way. So now that we've covered the error parts and what they are, transient, non-transient, now I have to switch gears and talk about processing semantics, right? So again, we showed the ideal world. Everything is processed exactly as they come in order, and exactly once, aka exactly once processing. You don't have to rationally think about the errors occurring, right? This is again the ideal situation, but the effect on the downstream system is this: the message came in once, I processed it, I threw it away, everything was good, right? But as errors start occurring, to adjust for these sorts of things, you might have to relax your processing semantics a little bit in order to tolerate these processing errors, right? Are you willing to give up some of these processing guarantees, such as in-order processing, things like that, in order to achieve a more resilient application? And it's important to know what some of these semantics are when you're selecting an error handling strategy. As I go through and classify them, I'll call out what processing semantics they actually support, right? So this is the 4 different types of processing semantics. Again, exactly once is the ideal situation. This is if your application requires this, you cannot tolerate data loss, you cannot tolerate duplicate data, and the process's effects on the downstream system as if the message was processed exactly once. So again, if you're doing a database update, the record comes in, you don't miss anything, you don't have duplicate records in there, and you've inserted 1 record into the database per message. Now, effectively once is similar, but it will tolerate duplicate data. You still can't tolerate any data loss, but you can tolerate duplicate data as long as the reprocessing of data or duplicate data has the exact same net effect as if you process the message once. So if you're doing an insert of the same record twice into the database, that would have the net effect of if you processed it once, as long as you're not changing it after the fact. If it's just a strictly insert, if you process 3-4 times, it's going to be okay. The state will look as if you processed it in once. That's going to be effectively once processing semantics. Now, at least once is where you can, again, you cannot tolerate data loss, but you can tolerate processing the data more than once. And this is okay. These are things where you can just sort of handle these situations. You're okay with duplicate data, but you cannot lose data. And you'll deal downstream in the applications. You'll deal with the duplicates later on. And then the least restrictive is the at most once, right? This is the best effort. I'm going to send you the message. Try to process it. If not, I'm not going to resend it again. So there's the possibility of data loss or unprocessed messages, and you will never have duplicates because you're never sending the same message twice. So incomplete processing of messages is possible, and these are the different semantics that will be provided by these error handling patterns, as we talk about in the rest of this presentation. So now I want to talk about this demonstration framework. I wanted to do this first. I spent a lot of time developing this code here, and it's all available on this GitHub repo. It's publicly available, and I've developed this framework in such a way so that you can easily see for yourself how these different error handling patterns work as you change configuration settings in Pulsar to process messages differently, what the net effect will be as far as what the in-order processing, how they were processed as far as in order, how many times they're reprocessed, if they end up in dead letter queues and things like that. So this is all available, and it's available to test different things, and we'll talk about this shortly. But I want to cover with the goal of being, I wanted to set up a framework in such a way that I can show the different patterns all using these 3 different scenarios that go back to the error types, right? So you will have a non-transient error with very limited scope, where you have bad messages, right? So if messages come in with the contents of 13 and 42, we'll pass this through each one of these error handling patterns and see the results. How do the messages get processed? What's the net effect on the systems? These are, again, every time it sees an error, the message with this value, it's just going to error out. Again, it's to mimic a bad or corrupted record. Second scenario would be an external system outage. So again, when the 11th message comes in, it's going to trigger that's to signal to the system to act as if an external system like a database is offline, and it stays that way for 15 seconds. It will continue to try processing messages during this time, but it will not be able to reach that external system, and so we'll see how these error handling patterns behave in this scenario. And last but not least, we'll have a more transient networking issue wave where every 9th and 23rd message, again, I just pick some random numbers to spread it out a little bit, and this is completely configurable. We'll see how this is in the system. But these network happen very more commonly, more frequently, but they clear also more quickly every 3 seconds, right? So the ninth message comes in, it will act as if the network is unavailable for 3 seconds. Then when the 23rd one comes in, the 18th message and the 27th and so on and so forth, there's going to be just waves of disruption, and we're going to see all these different how all these different patterns behave in these scenarios. Now, at a very high level, before I get into the code, I just want to say that it's implemented as a REST API, so we're going to get an endpoint where you can connect and very easily test these various error handling patterns by providing different parameters. Under the covers, it's implemented as a Spring Boot application with the five error handling patterns pre-configured. Obviously, you can change the behavior. It's there. Obviously, once you take it, download it, expand it, add some new scenarios, however you see fit. Has configurable error behavior as well, as we'll talk about there in a little bit, so I can mimic transient, non-transient errors. And then as an output, it returns a JSON. So it's a REST endpoint. You get a JSON message back, and it contains 3 subset of categories. The process messages, and that's retained in order, so you can see exactly how they were processed on the system to see if in-order processing was guaranteed or not. The number of times each messages was processed, so I keep track of it for detecting reprocessing of messages. And if you have a dead letter queue enabled, what messages ended up there in that dead letter queue. Okay, so let's discuss some of these error handling patterns that I have hard-coded into that framework that I just showed you. Right, so the first one that we have is the easiest one, stop on error pattern. This is probably the most simplest one to do. Basically, when an event comes in, the first time you see an error, you stop processing it. Right, so this is useful when all input events must be processed in order. You must maintain the order, and you must have 0 data loss. One example use case would be if you're handling change data capture log information, streaming in from a different database, and you're trying to replicate that to another database. The order of the processing is critical. Maybe processing log files and putting them back together line by line, putting them back together, something like that. So as soon as an error occurs, you flip a circuit breaker, and this is showing you that the consumer stops processing the messages. And there's pros and cons to this, right? And some of it is you get exactly once processing semantics, may be delayed, but you definitely process it just once, and you're maintaining in-order processing. Last but not least, it's fairly easy to implement from a coding perspective, but there are some big trade-offs. First being that when the error occurs, you're going to have a large backlog of messages while you're trying to resolve the issue. And typically, once you've triggered the pausing, which we'll show here in a second, it requires some sort of manual intervention to restart the application processing from where it left off, which in turn implies that there's an alerting or notification mechanism required for that. And the other thing is, once you stop processing messages, there's an implied latency penalty for all of those messages from that point forward. So if it takes you 10 minutes to resolve, if your mean time to resolution for that error is 10 minutes, then your processing time from the time that message occurred until you process it is whatever it is plus 10 minutes because of that latency while you're fixing things. So these are the trade-offs that you have in place. To do it, again, it's very easily. You can go back to those patterns that I showed you in the framework. You could really just not catch an exception and let it be thrown and crash your application. Not graceful, but would have the same net effect. Instead, I recommend using this pause command that's built into the consumer interface. You're basically saying, hey, pause. I don't want to get any more messages. You're not going to fetch any more information from the broker, but you will continue to process messages that were in your receiver queue. So if you look back in the code for this, I intentionally set the receiver queue to 1. And this is why, as we're looking at some of these observed behaviors, and we'll walk through some of this. I'll walk through one later, not this particular one, but to show you this, is that even though we threw the exception, so remember those bad messages occurred first, we actually got that message and then stopped, right? So message number 11 was supposed to trigger it. We should have only processed 11 messages, but we processed one more, because there's one still sitting in the receiver queue, so be aware of that. That if you put this in the code and you definitely don't want to even process that additional message, then if you put a pause in here, you also should probably set an internal flag and check that as well, because the system will continue to pull the messages off on there. Now for everything else behaves as expected. The external system outage happens at a certain message. Boom, so everything after that point, the 77 messages out of the 100 do not get processed. Multiple messages, no messages are reprocessed, you just stop. This is universal for this pattern. Same with the intermittent networking issues. It happened on message number 9, so the first 8 were processed. Boom, it stopped. I think this behavior is slightly different because of the duration of the framework, so it might be an impact of the framework here as well. But just let you know that it stops. So as soon as you process up to the number of messages where the first error occurs, and then that's it. Everything beyond that point is unprocessed. Nothing is reprocessed, and messages after the first error occurs are left that way. A similar simplistic approach is the ignore error pattern, which is kind of similar. So an error comes in, you're never going to toggle it though. You're just pulling information in, and if it's an error, something happens, you're just going to drop it. Just say, okay, this one I can't process, I want to keep going, right? So this is obviously going to introduce potential for data loss, but it's useful if you have the use case where you want to process information within a certain time frame. So you don't care if you process all the information as long as you process the most recent. So a use case might be you're having feeding incoming sensor readings for real-time anomaly detection. You're more interested in having the most recent sensor reading and making a reaction based on that, rather than having processing data that's 2, 3, 4 minutes old when there's a newer sensor reading that supersedes that one. So this is a good example for that. And this guarantees that you never get stuck processing. There's no delay on that. These are some of the trade-offs. But again, this is implementing the at most once processing semantics. I'm going to send it, you process it, maybe you don't, there's data loss, who cares, but there'll never be duplicates. You don't get the backlog that you have with the stop on error. Guaranteed lower processing latency, you're consuming as fast as you can. You will process them in order, just not all of them. So again, you might process an incomplete data set, but they will not be out of order. And again, it's fairly easy to implement. And as I mentioned, data loss and obviously incomplete or data set can be occurred. So if you're doing calculations on that, bear that in mind. These are some of the trade-offs that you have. Implementing it in Pulsar is as simple as this. No matter what, regardless if you get an exception or not, this is success or failure, always acknowledge them. Like whatever happens, boom, I got it, keep going. Don't negatively acknowledge it. Don't let it sit there. Just send an act back and you're done. This is really it in that regard. So again, if we ran the scenario through, it works as expected for bad messages. 98 out of the 100, only the 2 bad messages are ignored. When you have an external system outage, again, it maps directly to the time that the system was offline. So you get 100 messages in at message number 15 or whatever. There's an outage. It's out, or 11 rather. It's out for 15 seconds. Since we're sending them in 1 per second, those 15 messages are lost. But then you get the next messages are there. They're all processed in order. And then with intermittent networking issues, the same thing. You just have waves and waves of errors. So you're going to drop and ignore more messages, but nothing's reprocessed. You just have a higher drop rate basically. So again, as this is the expected behavior, more errors result in more drop messages. But all the errors get processed in order. All the messages get processed in order rather. Now, the most simplistic way of doing a message retry in Pulsar is obviously knacking these sort of things. So the source and the retry topic are conceptually here one and the same, and that's what it does, right? So if you can't process it right away, something's going on, you send a knack back, and this lets Pulsar say, hey, I'm going to send it back after a certain amount of time, sends it back in the queue, right? So it's useful when in-order processing isn't critical, but there's a high probability that the error is transient in nature. Right, so like again, this is the, hey, I'm trying to publish something. I'm looking for a system. I'm doing an online order. I'm doing a lookup in a database, and it's not there. Maybe there's a race condition. Something didn't write to that. The stream processor that was writing to that database didn't write it yet. So if I wait 30 seconds, come back and look, I'll probably find it. So let's just delay delivery the messages, sort of thing. and we don't have to have a special call out queue for that. So this is your traditional message retry on this. Again, it has the advantages of at most one processing semantics. You're going to either successful or not. It again avoids the large backlogs. You don't get stuck on a message. You send it back in certain scenarios. It's easy to implement, but you can have out of order processing, right? So now that you're knacking it, sending it back, it could be, potentially your messages are going to get out of order in an error scenario. So that's something to bear in mind. And if the error isn't transient, as we'll see with the bad messages, the error never resolves itself as a corrupt message. If you don't account for it, then you have infinite message redelivery eventually, right? I knack the message over and over again. It just keeps bouncing back and forth between the client and the server. So if the error scope is broad, then you start getting some backlog, right? If everything you fetch in, if you have a buffer full of 1,000 bad messages for whatever reason, let's say you had lost an encryption key, every batch of 1,000 messages you come in, you knack them, they're going to send them right back, right? So you're never going to resolve it. You could eventually get backlogged or even stalemated in the scenario because you're not making any progress at some point. Because if your queue fills up with knacked bad messages that are unresolvable. From an implementation perspective, it's as simple as on an exception, I send a negative acknowledgement. That's it. And in the configuration, you have not made any adjustments for dead letter queues or retries or maximum number of retries. It's just basically I'm going to knack it, and that's it. So that's the scenario. Again, I'll show you one of these here at the end about doing the diagnostics on this. But again, acts as expected for the bad messages. The two bad messages were continuously knacked though, right? So they bounce back over a period of 5 minutes. The messages that could be processed were the two bad messages that could never be resolved were continuously sent back and forth, ping-ponged 20 plus times each. There were bad messages, and then they were continuously knacked, and so eventually I had to stop it. It would never have resolved in that queue. Similar thing if on the external system outage, there were some messages that the outage was out for 15 minutes for an extended period of time, so there are many reprocessed messages. I'll talk about this one here in the next slide about how the dead letter queue did differently on this, but there was 17 that were being knacked back and forth, and right, so we were waiting for a minute at the end, but the knack delay was 30 seconds, 40 seconds, and so there were some messages that didn't get processed simply because we had knacked them, but we ended the test before they got redelivered one more time, while the error condition was still available on that. Now, with intermittent networking issues, everything got through, so that wasn't an issue. I have to look into some of those examples on that. Messages were processed out of order, but eventually everything got delivered because the errors were clear themselves enough. It was a smaller outage. And so, because I think the knacks are frequently delivered, and they didn't fail enough that they got kicked out. So expanding on that pattern is in obviously if you have a knack, so you don't have that continuous redelivery scenario, then you want to have what's called the dead letter queue pattern. Again, after a predefined number of processing attempts, so you do like you did before. I try to process it. If it's an error, I send a knack, but after a certain number of times, I give up. And after 3 times, 5 times, whatever, I throw it to a dead letter queue, just get it out of the system. I'll look at it later. This is a perfect example for, bad messages that are never going to resolve themselves. And you want to avoid the infinite redelivery, reprocessing of messages, move them to an offline queue, and clear the situation. So it solves that problem quite nicely. Similar advantages as the previous one, I won't get into it, but there's a finite number of redeliveries. That's one of the advantages over the knack one or just the retry without dead letter queue. After so many times you give up, easy to implement. Again, you're going to get out of order processing because you're redelivering the messages, so your order processing is broken. But you could get a large backlog of DO in your dead letter queue if the error scope is broad and the majority of these messages are knacked repeatedly. Then it could fill up you could basically shift all your data into the dead letter queue in a really prolonged scenario where an external system is out for hours, then you'd fill out your dead letter queue up with an hour's worth of data, whatever your publish rate is, and that could be very bad as well. So this is done strictly through configuration as well as the NAC. So it's implied that you do the NAC, as we showed in the previous one. We get an exception, you throw a NAC. But here you specify the dead letter queue policy. You can specify, what you want the topic name to be, and the maximum number of redeliveries. In this case, I think I did 3. So I'll give it 3 tries. After 3, I just throw it into the dead letter queue, and that's it. And again, this works. Must be a shared subscription type, same as the retry. In a minute, you cannot do this on exclusive because it will block scenarios. So let's just, and then I aggressively tweaked the negative ACK redelivery, or the ACK redelivery delay. So every 10 seconds, if I NAC it, it's supposed to wait 10 seconds to send it to me again. So as expected for the bad messages, we send 2 pieces of bad data in. They're the only ones not processed. They both end up in the dead letter queue. During the external system outage, again for a 15-second wave, most of them got through. Many redeliveries bouncing back and forth many times, but a total of 4 of those weren't processed, and they ended up in the dead letter queue again because they exhausted the NAC delivery. Right, you send them back, waited 10 seconds, send them again, send them again. It failed in that scenario, and they were sent to the dead letter queue because they had 4 attempts, and the limit was set to 3. And then again, as you had intermittent waves of errors, less messages got through. More of them got trapped in the system where the networking was down, where simulated the network would be down for an extended period of time. So more of them obviously got retried and failed, and more of them ended up in the dead letter queue. And so it's in line with what our expectations are. And again, we'll walk through some of these at the end. I think we can do that here after this next slide. I'll go through an example of one of these one of those JSONs in detail with a jQuery and show you what it works. But the last but not least, so the ultimate one, building on these ideas, is here's the retry queue pattern. And here you've now, up until this point, we were using the retry topic and the source topic were the same. Here you have a completely separate retry topic, right? And so you go through the same processing. I forgot to draw the arrow here, so please forgive me, but you're pulling out the message, processing it. Is it an error? No, you continue to just affect the downstream system. If it is, then you check the max retry. Have I tried enough? No. Rather than keep it in the source topic, now you put it in a retry topic, but you also specify the reconsume later. You say, hey, I'll process this, but wait 10 seconds, wait 20 seconds, wait 30 seconds, specify the time, and then that stays disconnected until a timer triggers it and it closes it, and it consumes that messages again. If it still fails after X amount of attempts, off to the dead letter queue it goes, just like everything else. But it has an additional, you can pause it, so you don't have to worry about it being controlled by the NAC frequency, and you have a more predictable delivery rate. If you know, for example, the database is down, or this particular system is down, you can send it there for a couple hours and just get out of the queue and process other things. So again, some of the pros and cons. As before, again, you're only going to process each message once, avoiding the lower latency. Finite redeliveries can be combined with the dead letter queue. You can specify more granular control over when the messages get redelivered. Again, you can get a large backlog in the retry topic if things are down and you want to pause them for a very long period of time. This is implemented through configuration exclusively as well. So when you go back to this framework, you want to go into the consumer configs, tweak these or add these different properties. Everything is inside the dead letter policy builder. Dead letter topic, retry topic is what you add there, and then your redelivery count. And that all works together in conjunction to implement the pattern we just saw. We'll break out here, stop here, and show some of these examples to get a detail what it is. But again, with the bad messages, just as expected, the 2 bad ones end up in the dead letter queue. Everything else makes it through. Bad messages were bounced back and forth a little bit until it was finally given up, and that's it. External system outage, almost identical to what we saw with the dead letter queue only. Prolonged period of time, messages got redelivered, resent, reprocessed maybe isn't the right word, resent, redelivered messages multiple times. And then unprocessed messages, again, those that failed, all 15 of them end up in the dead letter queue, so we have 100% accounted for. Same with the intermittent. Again, this was really happening quite a bit, much more frequently, and this seems to be that are redelivered right away. At least that's the observation I had when I was looking at that. So send them out, you say reconsume 3 seconds later, and they're aggressively getting resent. And so they would quickly die because they would expire during this outage window. So let's quickly pause here, and I'll go through one of these examples to give you an idea of what we saw in detail. Again, for each use case. So again, this is the retry topic pattern. This is the last one we looked at during the use case of the external outage, and then we're going to run the jQuery through. So the first thing you can see is that it processed the 85 messages, and then we display all the messages as they were processed in order. So it was taking it and publishing the message out to the topic, and this is the order they were processed. So you can see up until the outage occurred at message number 11, which triggered it, and it stayed in the next 15 seconds of outage, where the next 15 messages 11 through 25 came through, were missed. They were just skipped. And then from that point forward, from 26 onward, you can see all the messages again were back in order. Everything was sent out. So this is a great example. You just carved out those messages. Here we can see the messages during that time, 11, 12, 13, 14, were processed multiple times. Processed again meaning the consumer said receive, got the message, was unable to do anything with it because the error conditions still occurred, and so it had to negatively acknowledge it again. So each one of these were nacked 11 times, and since they all exceeded those particular redelivery counts, they ended up in the dead letter queue as expected in the order they were processed. So in summary, I introduced a framework for testing the error handling patterns in Apache Pulsar that can mimic both transient and non-transient error conditions, and showed how to use that framework to run the same 3 test scenarios against 5 different error handling patterns and examine some of the results. I also discussed these results as long as how to implement these various error handling patterns, some of the pros and cons of each one, and some of the different use cases that would be applicable for those. And last but not least, I discussed some of these error results in detail for each individual pattern and how they've lined up with our expectations. Thank you very much. Hope you enjoyed the talk.